In today's video, we're going to look at the graphs of the sine and cosine functions. So by the end of today, we should be able to draw the graphs of the sine and cosine functions. We should be able to acknowledge the difference between the graphs of sine and cosine and the unit circle representations of these functions. We should be able to see the properties of sine and cosine and how they manifest on the graphs. And we should be able to use the graphs to recognize that cosine is actually just a horizontal shift of sine. Now, in the previous couple of days, we introduced 4 other trig functions which also have graphs, but I would say that they are not nearly as important as the graphs of sine and cosine. So we're just going to have a quick look at the graphs of the other 4 trig functions. We're not going to study them in too much detail. Okay, graphs of functions. A graph of a function is just a visual display of the relationship between the inputs and the outputs of a function. So for example, if you had the function f of x equals x squared, for example, then the graph of this function would be drawn on the xy plane. Horizontally is where we would represent all the inputs of this function, all the x values. And vertically is where we would represent all the output values of the function, all the y values, one might say. So in order to construct a graph from scratch, the traditional technique is to plug in several different inputs, figure out the corresponding outputs, and then plot those points on the xy plane. If I plug in x equals -1, then -1 squared is +1. So to reflect that, I would plot the point where x is -1 and y is +1. This point indicates a relationship between an input of -1 and an output of +1. If I plug in x equals 0, 0 squared is equal to 0. So I would plot the point 0, 0, and this would tell the reader that for this function, if I plug in 0, the output is going to be the height of the point, which is also 0. Same thing is true for +1. +1 squared is 1. So if I plot the point 1, 1, this tells the reader that if you plug in an input of 1, then the output will also be 1, and so on and so forth. And then by sort of connecting the dots, connecting the dots better than that, by connecting the dots, you get a visual relationship of all the inputs and all the outputs for this function. Any point on the graph is a piece of data about an input and the corresponding output. So when I graph the sine function, I graph this in 2-dimensional space as well. The horizontal axis, when I'm graphing the sine function, the horizontal axis is representing the inputs of sine. The inputs of sine, that is angles. So it would be appropriate for me to decorate the horizontal axis in the graph of sine with values like 0 and pi/4 and pi/2 and pi, which would be 2 steps away in the scale, etc. As well as things like -pi/4, -pi/2, -pi, etc. It would be appropriate for me to label the horizontal axis with these values because these are angles that would typically be plugged into sine, and the horizontal axis in the graph of a function represents inputs for that function. What is on the vertical axis? The vertical axis contains outputs of sine. The vertical axis contains y values on the unit circle corresponding to all these different angles. So let's see if we can plot a couple of points on the graph of sine. I'm going to represent the inputs by theta and the outputs by sine of theta. And let's see, for example, what we get if we plug in theta equals 0. Sine of 0, looking back at our unit circle, is equal to 0. So I would plot the point 0, 0 on the graph of sine to say, hey, input is 0, and at that location, sine outputs 0 as well. If I plugged in, for example, the angle pi over 4, then sine of pi over 4 is equal to the square root 2 over 2, which is roughly speaking 0.7. So I would go on to the picture, and let's say maybe this is like positive 1, so that 0.7 is right underneath it, maybe about here. I would plot this point on the graph of sine, and that communicates to the reader that if I plug in an input of pi over 4, the corresponding output is approximately 0.7. What if we went to, for example, pi over 2? If I plug in the angle pi over 2 to sine of pi half points straight up, so sine is positive 1. And so I would plot the point where the input pi over 2 was the horizontal component, and the output of 1 was the vertical component. By drawing this dot on the graph, what I'm communicating to the reader is that if I plug pi over 2 into sine, then 1 is what comes out. This little dot on this picture carries exactly the same information to the reader as if I said sine of pi over 2 equals 1. Now I can continue to fill in dots by hand and connect the dots, and when you do that, you get a shape that looks a little bit like a wave. Now this is a fairly rough handmade graph, so let's go ahead and grab a computerized graph real quick so that you can see this more clearly. So here I am on Desmos showing the graph of the sine function, and we can already see that the computerized graph agrees with what we have found by hand so far. We have found that the graph of sine goes to the point where the input and the output are both 0. We also found that sine goes through this point where if I plug in pi over 2, sine outputs positive 1. And we see a few other results that are consistent with what we know about sine from all the work that we have done up to this point. If you plug in negative pi over 2 instead of positive pi over 2, then the output is negative as well. Now from the graph, you can see reflected quite a few of the properties of sine that we already studied in the previous couple of sections. The first of which is the fact that sine is an odd function. We determined that sine was an odd function by evaluating the relationship between sine of negative theta and sine of positive theta. Odd functions, their graphs had the property that if you rotated them 180 degrees, then you would get exactly the same picture that you started out with. And we can see that in this picture as well. If I rotate the graph of sine 180 degrees, then the result of that will be exactly the same as it was when we started. I wonder if I could show that in the video. If I can figure out my editing skills, I will try and show this graph rotating. We'll figure that one out later. Another thing that you can see in the graph of sine is that if you move 2 pi units away from the starting position and move to a coterminal angle, Then if you move 2 pi units away and move to a coterminal angle, sine behaves exactly the same 2 pi units away from any angle. If you plug in 0, that's the same thing as plugging in 2 pi. If you plug in pi half, that's the same thing over here as what you're getting from 5 pi over 2. Here, if you plug in 3 pi over 2, that's the same output as what you get from the coterminal angle of 5 pi over 2. 7 pi over 2. So in this picture, we can see the fact that if you increase or decrease an angle by a full rotation, then sine is going to output exactly the same value. So you can see that by the fact that the graph repeats every 2 pi units. Similarly, we can construct the graph of cosine, which would also be a visual representation of all the inputs and outputs of this function. When we graph cosine, we have to be a little bit careful. Once again, when you graph a function, the horizontal axis is being used to display inputs for your function. Inputs of cosine. And inputs of cosine are always angles. So in the graph of cosine, once again, we would be plotting values like pi half, like pi, like 3 pi half, etc. When we graph cosine, the vertical axis is always used to display outputs of cosine. So the horizontal axis is an angle. The horizontal axis might be appropriately labeled by theta or alpha. In the graph of cosine, the output is the x-coordinate on the unit circle, and that is what is being shown vertically. So a point that would be on the graph of cosine, one point would be the point 0, 1. This point is on the graph because if I put an input of 0 into the function cosine, the number 1 is the output. The graph of cosine passes through the point 0, 1 because if you plug 0 into cosine, the output is 1. If I plug pi over 2, 90 degrees into cosine, the output is going to be equal to 0. We also know that cosine of pi points to the left side of the unit circle, so the output is -1. And on the graph, we would represent that by plotting a point whose horizontal value was pi, and whose output was -1. So if you begin to connect the dots after drawing more and more of these inputs, you begin to get this same wave shape that we saw for sine. Again, this is hand-drawn and is a little bit messy, so let me go ahead back to Desmos to show you the computerized image. Alright, here is the computerized graph of cosine. Once again, we get the same results from the computerized graph that we got from our hand-drawn analysis. Namely, the function passes through the point 0, 1, because if you plug 0 into the function, the output's 1, and it passes through pi over 2, 0, because if you plug in pi over 2, then 0 comes out. Looking at this picture, we can also see visual confirmation of the fact that cosine is an even function. Even functions graphically had the property that they were exactly the same on the left as they were on the right. The left and right halves of the graph were mirror images of each other, and we can see that manifested in cosine. Cosine, just like sine, also has this property that its graph repeats every 2 pi units. Because of this property, that cosine outputs exactly the same value at coterminal angles. So if you start at 0 and then you go 2 pi units to the next coterminal angle, the outputs of cosine will be exactly the same. If you go from pi half to its next coterminal brother, 5 pi over 2, again, cosine is doing exactly the same thing. So you'll see the graph repeat every 2 pi units. Now if we graph sine and cosine together on the same axes, we can see that their graphs are actually extremely similar to one another. Actually, they are identical except for the fact that the graph of cosine and the graph of sine are slightly offset from one another. They are horizontal shifts of one another. So I do recommend actually memorizing the graphs of sine and cosine. To at minimum memorize the fact that the graphs are these infinitely repeating wave patterns that bounce between -1 at the lowest and +1 at the highest. That's worth memorizing. We'll work with these graphs quite a bit more as time goes along, so you'll probably end up memorizing it by accident. But it's a good graph to have in mind when you're going into calculus, calculus 1 and 3 in particular. Now, one of the trickiest things about getting started working with the graphs of the sine and cosine functions is that there's a big difference between the graphs of these functions and how they are represented on the unit circle. Both of them are ways of visually representing sine and cosine, but they are fundamentally different representations. On the unit circle, angles are represented by literal angles drawn in the circle. So if I wanted to represent an angle in the unit circle image, I would literally have to crank through an amount of turning that is given by the angle alpha that I'm considering. On the unit circle picture, the outputs of cosine are represented by the x-coordinates on the circle. So in other words, in the unit circle representation, the outputs of cosine are the horizontal values. And in the unit circle representation, the outputs of sine are represented by vertical values, or the y-coordinates on the circle. So in the picture of the unit circle, it would be appropriate for me to label the horizontal axis by something like x equals cosine of whatever angle you're working with. The horizontal axis represents cosines in this picture, and the vertical axis represents sine values in this picture. Sine and cosine with alpha plugged in. Now, if you're looking on a picture which contains the graph of sine, in this case, the horizontal axis has a completely different meaning than it did in the unit circle picture. On the graph of sine, the angles are represented by horizontal values, and the sine outputs are represented by vertical values. So it would be appropriate for me to label the horizontal axis by something like alpha and the vertical axis by something like alpha. And on the graph of cosine, again, a different picture, and the axes have a different meaning. In the graph of cosine, the angle values are represented horizontally, and the outputs of cosine are represented vertically. So it would be appropriate for me to label the horizontal axis by alpha and the vertical axis by cosine of alpha. So working with the unit circle versus working with the graphs of sine and cosine, you do have to be careful to know exactly what is being represented on the horizontal axis versus what is being represented on the vertical axis. It's just like when you're working with any other kind of chart. You know, on the one hand, I could look up a chart to see how many people are using steam at any given time, which remarkably has a sinusoidal pattern, apparently. Now, in this particular chart, the times are being displayed on the horizontal axis. Values on the horizontal axis represent times. Values on the vertical axis represent the number of users of this particular game on Steam. But as soon as I switch to a different chart, for example, a chart showing how many cases of COVID have been encountered in the US in total, this is a chart that's similar in nature. I mean, it has a horizontal axis and a vertical axis, and it has a squiggle that is drawn on that picture. But the meaning of the stuff in this chart is completely different. The values on the horizontal axis no longer represent times, now they represent days. And the values on the vertical axis no longer represent how many people are playing this game, now they represent how many people have come down with COVID. And that's what we're seeing here. Two visual representations that are a little bit similar in nature, but they are two totally different images, two totally different charts. And the meaning of the stuff on the horizontal axis in each chart is different. The meaning of the stuff on the vertical axis in each chart is different. So be careful about that. One of the reasons that I've gone so hard talking about this issue is because it's really common for students to make mistakes, getting confused between the unit circle representation of sine and cosine and the graphs of these two functions. Here's a quick animation showing the relationship between the unit circle and the graph of sine. In the graph of sine, the angle is drawn on the horizontal axis, and so as the angle increases, you can think about basically traveling along the horizontal axis. In the unit circle, the output of sine is represented by the y-coordinate on the unit circle, and the output of sine in the graph is represented by the y-coordinate on the graph. So to finish up, let's just use the graph of sine and cosine to answer a couple of questions. For example, someone asks me, what is the domain and range of the sine and cosine functions? Now recall that the domain of a function was the collection of all its possible inputs, and graphically this would show up as all possible horizontal values on the graph. That's because the horizontal values on the graph of a function are representations of the function's inputs. The range is similar, except the range is the description of all possible outputs, and graphically this would be represented by all the possible vertical values on the graph. So let's have a look at the graphs of sine and cosine one more time, and let's see if we can describe all the possible horizontal values that we're seeing and all the possible vertical values that we're seeing. Here I am back on Desmos looking at the graph of cosine. Now let's have a think about this domain. No matter how far I scroll to the right, no matter how far I scroll to the left, the graph carries on infinitely in both directions. The graph does not have any holes, asymptotes, breaks, jumps, etc. The graph continues smoothly, infinitely to the left, and infinitely to the right. So as a result of that, I would say that the domain of cosine goes from negative infinity all the way to positive infinity. The domain, based on the graph, negative infinity to infinity, aka all real numbers. Let's have a look at the range of cosine, which would be all the possible vertical values that we're seeing on this graph. So here in the visible portion of this picture, we can see that the vertical values never go above 1. Here's 2, this is 1, and this is the highest that cosine can reach. On the flip side, we have negative 1, which is the lowest that cosine can reach. And because of the repeating nature of cosine, that is true no matter how far we scroll to the left or the right. The values, the output values, are always bounded between 1 at the top and can't go below -1 at the bottom. Here I've made a note of the range. The range goes from -1 at the bottom. Cosine can reach -1, but it can't go below that. And it can reach 1 at the top, but it can't go above that. So those are the range of output values for cosine. Now what about for sine? If I graph sine, because it's really only a horizontal shift of cosine, we still get the same domain stretching all the way from -infinity over to +infinity, and we still get exactly the same range, going from -1 at the lowest to a +1 at the highest. Now this makes some sense based on the unit circle representations of sine and cosine. Because the inputs of sine and cosine are angles, and you can draw any angle, it makes sense that you can plug any angle into sine and cosine, and you get a domain of -infinity to infinity. Because sine and cosine are values on the unit circle, and the unit circle has a radius of 1, it makes sense that sine and cosine can never go below -1 or above +1. So I would recommend not necessarily memorizing this domain and range. You can always go back and figure these out again by thinking about the unit circle or by looking at the graphs of these two functions. We're almost done. Just a quick note that I have in the notes summarized some of the observations that we made as we were looking at the graphs of sine and cosine a few minutes ago. For example, the fact that sine and cosine repeat every 2 pi units, the fact that sine is an odd function, and you could see that in the graph, and that cosine is an even function, and you can also see that in its graph. So I've made those notes here. The final thing that I would like to do is just very, very briefly take a glance at the graphs of the other 4 trig functions. Here is the graph of the tangent function. In this picture, the horizontal axis contains angles because angles are what is being put into tangent, and the vertical values are the outputs of tangent. So you see this repeating snake pattern. Cotangent is quite similar, except the snakes move in the opposite direction. They go down instead of up. Secant looks like a bunch of parabolas, some of which are pointing up and some of which are opening down. And cosecant is very similar to secant and also looks like a bunch of parabolas. This, as usual, can be obtained by hand by plugging various angles into these functions and plotting their outputs. This concludes today's material. We reminded ourselves what the graph of a function is, what the graph tells us conceptually about the function, and then we used that information to determine the graphs of the sine and cosine functions. And we had to be really, really careful to make sure that we knew the difference between the graphs of sine and cosine and their representations on the unit circle. We got to see how some of the properties of sine and cosine show up and manifest themselves in their graphs. For example, evenness and oddness. And then we took a quick look at the graphs of the other 4 tangent, cotangent, secant, and cosecant functions.